So this talk is about a functional programming language called Numerical Fuzz, featuring a type system for rounding error analysis that's particularly useful for understanding the behavior of programs that evaluate floating point expressions. So for this PLDI audience, let me describe the purpose of a rounding error analysis, which is to derive an a priori bound on the effects of floating point rounding errors on an algorithm. But the problem is that sound tools that automatically perform rounding error analyses tend to give pessimistic bounds and scale poorly. By pessimistic bounds, I mean that these tools might often return to us that the error is upper bounded by infinity, which is generally not a useful result. And by scaling poorly, I mean that these tools usually only work on benchmarks with fewer than 40 floating point operations. So we can see an example of this problem in practice by considering polynomial evaluation. So in polynomial evaluation, we're given a value for the variables of the polynomial, as well as all the values for the coefficients, and we're asked to evaluate the polynomial at those values. Pretty simple, right? And you might recall from earlier on that in your education at some point, maybe computer science, that a common algorithm for polynomial evaluation is Horner's scheme. So here we rewrite the polynomial using nested multiplications and additions in order to reduce the number of operations. So we can find an implementation of Horner's scheme in the NumPy polynomial library as the polyval function. And so here is the snippet of the documentation for that polyval function from that library. And we can see that in addition to saying that it evaluates a polynomial at specific values using Horner's scheme, we also have the following warning from this documentation: that for polynomials of high degree, the values may be inaccurate due to rounding errors, and that we should use this function carefully. So that may or may not be a very helpful snippet of documentation in the case that you want to use this function, right? And it probably brings up a few questions, but the one that's most important for this talk is actually how inaccurate should we expect this result to be? Okay, so the issue at hand here is that Horner's scheme is an algorithm that's assumed to operate on real numbers, and all of our operations are assumed to be infinitely precise. But polyval is a floating point program operating on floating point numbers, and all of the operations are finitely precise floating point operations. They are not infinitely precise. So the semantics of a floating point operation is that it should behave as if it's computed in infinite precision and then rounded to fit in a format. That's what this little diagram shows. And every time the rounding for the results of a floating point operation occurs, some error is incurred. Now, if we're working, for example, in binary 64 or double precision, we know an upper bound on that error. So it should be something like 2 to the minus 53, depending on the rounding mode and some other details. But this only tells us the error associated with a single floating point operation, right? And our polyval function is the composition of many such operations. So we still need to answer this question of how inaccurate should we expect the result to be. Now, if I were to turn to the literature to try and answer this question, I would immediately run into our original problem statement, that existing tools tend to generate pessimistic relative error bounds. Okay? So in this table, I have the relative error bounds listed from two tools from the literature, FP Taylor due to Soloviev in 2018, and GAPA due to Melchion in 2006. Okay, and we're looking here at benchmarks of Horner's scheme applied to polynomials of increasingly high degree. So Horner 2 is Horner's scheme applied to a second order polynomial. There are only 4 floating point operations. That's what that second column shows there. All right. And what we want is for these relative error bounds produced by these tools to match this target relative error bound. That's like the theoretical worst case relative error bound. It's known in the literature if you open up a numerical analysis textbook. But you can see, and maybe it's been a while since you've seen scientific notation, but the best performing tool there is 5 orders of magnitude off. 5 more orders of magnitude greater than our target relative error bound. So that's not going to provide you with a useful error bound in practice. Okay, so our contribution to solving this problem is Numerical Fuzz. It's a functional programming language featuring a linear type system for rounding error analysis, and it's sound, it's useful, and it's fast. So, how does it work? Well, it combines 2 key ingredients: a local rounding error analysis, which tells us the rounding error produced locally by a function, with a sensitivity analysis, which tells us how functions amplify errors from inputs. Sorry. Okay. So, to understand how a local rounding error analysis works, let's consider a function f here that takes a numeric value as an input and returns a numeric value. We can conceive of f as having two different semantics, and that's what this diagram here is supposed to show, so keep that diagram in mind. An ideal semantics, where all of the operations in the body of our function are assumed to be infinitely precise, and a floating point semantics, where all of the operations in the body of the function are assumed to behave like a floating point operation, so that is, they're computed in infinite precision and then rounded to a destination format. The local error is then the difference between the results of applying f under its floating point and ideal semantics to the same value. So our key idea in numerical fuzz was that local rounding error behaves like a computational effect. So if we think of effects as what programs produce during evaluation other than values, then floating point programs produce values and rounding error. So in our work on numerical fuzz, we used a graded monad to track local rounding error. And the semantics of the graded monad that we used was a novel contribution of our work, but I'm going to leave the details of that to our paper, and instead introduce here an intuition behind the syntax. Okay, so if we have a function that returns a value of the following graded monadic type, then it produces numeric outputs and at most q rounding error, where q is an extended positive real number. And you can see now we've replaced the local error here in our little diagram by this value q. That's the grade on the monadic type. But now we should ask ourselves what happens under composition. Okay, if you are someone who has developed rounding error analysis tools before, you'll say yes. What happens to rounding errors under function composition? This has been a challenging problem. So if I have our function f that produces at most q local rounding errors indicated by its type and is shown in the diagram there, and I have a function g that produces at most r local rounding error as indicated by its type and is shown in our diagram here, then what is the total rounding error of the composition of g with f? Okay, we do not yet have enough information to answer that question. We have a missing piece in our diagram. And that missing piece is how does g, under its ideal semantics, propagate the local error produced by the function f? So this is where we come to the second key ingredient of our work, which is a sensitivity analysis, which tells us how functions amplify errors from inputs. Now the key idea with a sensitivity analysis is C-sensitivity. And a C-sensitive function is one that amplifies errors in its inputs by at most a constant factor of C. So for example, again here in our diagram, if we know that our function g under its ideal semantics is, for example, a k-sensitive function, then we will know by how much it amplifies the errors produced locally by the function f. Now, the idea of C-sensitivity was first integrated into a type system by Reed and Pierce in 2010. So that is not the novel contribution part of our work. And it was integrated into a type system, and it first appeared in this fuzz programming language. So now maybe you see where we get our numerical fuzz name for our language. And in that work, they used a graded comonad to track C-sensitivity. And the application domain was differential privacy, so totally different area. And the intuition there is that functions that have the following graded comonadic type as an argument, values with this type, amplify errors by at most a factor of k, where k is the value there on the grade. And again, k here can be any positive real constant or infinity. All right, so now in numerical fuzz, we answer this question of what happens under composition for rounding errors using the combination of the local error analysis and a sensitivity analysis. So we know now if our function f produces at most q local rounding error, and our function g is k-sensitive in its arguments and produces at most r local rounding error, then the composition of g and f will be a k-sensitive function that produces at most r plus k times q rounding error. And this is actually guaranteed as a consequence of our error soundness theorem, which is our main soundness theorem in our paper. And it says that well-typed programs of graded monadic type satisfy the error bound that the type system assigns it. More formally, if E is a well-typed program with a graded monadic type where the grade value is U, then we know that E will step under an ideal semantics to some value V1 and under a floating point semantics to some value V2, and that the distance between these two values is upper bounded by the grade on the type. So that is what our soundness guarantee looks like. And now when I introduced the contribution of our work, I made 3 claims: that it was sound, useful, and fast. We've seen evidence that it's sound, but what about being useful and fast? So let's talk about our evaluation. We have a prototype implementation of a type checker for our language following a sensitivity inference algorithm due to Azevedo de Amorim and co-authors from 2014. And so here is a nice little program written in our language. It takes two arguments, x, and it's too sensitive in its argument x, and it takes an argument y. We have a floating point addition, a floating point division, and so what it's actually doing is dividing x by the sum of x plus y. Okay, and then our type checker, we run it on this program, and it tells us, it infers an error bound for this program. We have two floating point operations, and so it tells us that it's the error bound on this program is something like 4.4 times 10 to the minus 16. So that's nice. Okay, let's come back to polynomial evaluation, which we started off with. Numerical fuzz generates optimal with respect to the worst case theoretical error bounds results. All right, so again, here we're looking at Horner's scheme applied to polynomials of increasingly high degree. So all the way down here, we have Horner's scheme applied to a 100-degree polynomial with a total of 200 floating point operations. Now remember when I started off, I said, okay, most tools only work for benchmarks like with less than 40 floating point operations. So here, this is 200. Yay, numerical fuzz is great. Okay, and we'll see here, if we compare the results, the relative error bounds produced by numerical fuzz, to the theoretical worst case relative error bounds, it's actually optimal. Okay, we wouldn't want it to be any smaller than this. Then it would no longer be sound, but it matches those error bounds exactly. This is what I mean when I say that it's useful. All right, what about timing? So here we list the timing from numerical fuzz compared to these other tools. Timing is how long it takes for our type checker to infer an error bound. And you can see that even for this larger benchmark with 200 floating point operations, numerical fuzz produces an inferred error bound in 36 milliseconds. That's nice. It's fast. Great. All right, coming to my favorite table. So numerical fuzz scales to really large problems, and it's the only tool to generate relative error bounds at this scale. I think that's awesome. Okay, so here we have benchmarks of increasingly large size. Come down to the bottom one here, we have a matrix multiply between two 128 by 128 matrices, over 4 million operations. And we have our numerical fuzz bounds and our theoretical worst case relative error bounds. Again, open up a numerical analysis textbook, you will find those. We're within the same order of magnitude. Again, we wouldn't want it to be smaller than the theoretical worst case relative error bound because then it would be unsound. Our tool is not unsound, but it is useful. And then we're timing. Other than this last case, everything is under 10 seconds. Our last benchmark takes about 18 minutes. And so again, evidence for numerical fuzz being fast. Okay, so to summarize, our contribution is numerical fuzz. It's a functional programming language featuring a linear type system for rounding error analyses. It's sound, it's useful, and it's fast. It combines two key ingredients: a local error analysis, which tells us the rounding error produced locally by a function, with a sensitivity analysis, which tells us how functions amplify errors from inputs. And please see more details in our paper. I did not go into much detail in this talk due to time, but we have limitations to our system. That's important. We also have implementation details, a really cool metric semantics for our graded monad, and we also discuss how we can deal with things like overflow and exceptional values that occur during the evaluation of floating point programs. So thank you. That's it.
Questions? Hi, thanks for the talk, very impressive. Yeah. Do you have an idea or maybe already a characterization for what kinds of programs you actually nail the error bound for? Like you get the optimal?
Oh, beyond like polynomial evaluation. I mean, yeah, that seems to have like a very specific kind of pattern of computation where we're able to nail the error bound exactly. No, we don't have any like general result that says for programs with this specific kind of computation we will perform optimally. No.
Okay.
Yeah,
cool.
interesting
Thanks.
though. Thanks.
Would it make sense to apply numerical fuzz to itself?
To be honest, I'm not quite sure that I understand the question. So we write numerical fuzz programs. We write a type checker. Oh, I see what you're saying. Like, no.
Do you have any idea or examples of kinds of programs where the parameter C is not independent of the value that you're giving it, like that of the value of the input?
So are you talking about the function sensitivity part of this?
Yes.
is not independent, or is
Yeah, because here we are assuming that the amplification of the error is like independent of the value that we're giving as input to the function.
And sorry, to repeat the question you're asking, is there a case where we want it to be independent of the value or dependent on the value?
Dependent of the value.
Perhaps. I can't think of an instance where we would need that for numerical programs at the moment. Yeah. I mean, yeah.
Okay, thank you.
Mm-hmm.
Hi. So in terms of lots of fast implementations for transcendental functions, like inverse square root or signs, there's often like bit level manipulations or integer masks or whatnot. Would it be possible to extend this analysis to those types of functions? Is that already covered?
To transcendental functions and their implementations specifically?
Yeah. So
so there are limitations of our language. Our metric semantics kind of limit the types of operations that we can handle. So in particular, I have a few like appendix slides here. So we are kind of, we're computing the relative error. And so really what's happening here is like you do not want you don't want x in this relative error example to be 0, right? And so numerical fuzz right now, it can't do subtraction. So we can do addition and we can handle we can like do a square root. But for example, the implementations of transcendental functions, you need subtraction. But this is because we're focusing on a relative error analysis. So if we extended the language in the future, that might be possible.
cool. Super cool. Thanks.
Yep.
In the polynomial example, what is considered the inputs for the purpose of these error bounds, x or
Oh.
the coefficients?
All of those things, the x and the values of the coefficients. Again, because it's a relative error analysis, we have to give bounds on the inputs for the other tools. Numerical fuzz, this is the bound generated for like assuming all values greater than 0, just positive real numbers. But for the other tools, we assume inputs of like 0.1, so 1/10 to 1,000.
Okay, and then follow up. This means, is the sensitivity analysis being reused for like multiplication, addition, over the both arguments and so forth?
So each of the floating point functions would have like its own sensitivity guarantee, and then it would be used inside of the function body of any benchmark that uses it.
Okay, and then so for the multivariable ones, does this become like a norm of a Jacobian?
So we didn't do a multivariable polynomial here. It's just Horner's scheme applied to like a single variate polynomial.
If
You're
the
saying in the case that we
coefficients
did.
are an argument, right?
Yeah.
Then my multiplication sensitivity would have to involve an
The
error in
coefficient
either one.
values are only used once, though. And so the sensitivity, like, it's kind of like a resource usage where we're saying, so like if we go back here, this function uses the value of x twice, and so it's too sensitive in this case to x. So if you imagine the case of like any of the polynomials, we're only one sensitive in each of the coefficients, but multi-sensitive in the use of the variable.
I guess maybe let me ask you this. A times x
Yeah.
is what is its sensitivity?
One sensitive.
Okay.
Hi. It seems that this work doesn't support unbounded recursion. I wonder if it's easier to adapt this approach to unbounded recursion.
So we do not support recursion in numerical fuzz. So we have a higher order language, but we don't have general recursion.
I know there are some works about sensitivity analysis for unbounded recursion. So is there any challenges to extending this approach?
So I mean, in that case, you can imagine we might be able to give like a trivial bound to functions, like an infinite bound, right? But I'm not sure that it would be like informative for this particular application of a sensitivity analysis.
Okay, thank you.
Yeah.
Hi, thanks for the talk.
Yes.
A while ago, I read a paper that they used dynamic tracking to track the error of computations, and they found that a naive implementation of k-means would cluster things completely different based on rounding error alone.
Okay.
Would it be possible to extend your framework so that you could express this property in some way and improve your implementation of k-means as regards to error tracking?
Yeah, that's an interesting question. I think that it probably is possible, right? So the original application of the sensitivity analysis was for the fuzz programming language, right? And so there, I think they are able to like implement a k-means type algorithm. So I think that probably there could be some adjustment to the language to be able to deal with that sort of a problem. Yeah.
Okay, thank you.
Mm-hmm.
Hello, I have a question. How do you find the amplifier k, and what if the case that this k is does not exist?
Right, so if it's not a Lipschitz function, then we cannot give like a sensitivity bound to it. So the primitive operations in our language we prove on paper, like their sensitivity bounds and so on, and then this is guaranteed as it kind of is built up in our language.
Your work in your work, it guarantees that this K can be found, right?
So any of the primitive operations of our language have to be shown to be K, like have such a K exist.
Okay.
Yeah.
Thank you.
Mm-hmm. Done? Okay.
I think we're done. Let's thank Ariel again.